Hi, today we'll be looking at the rectangular approximation method, which is often abbreviated as RAM. So with this, we're doing Riemann sums and trapezoidal approximation. So with rectangular approximation method, we use it to approximate the area under the curve over an interval from A to B. And we essentially do this by creating rectangles under our curve. Now, there's three different rectangular approximation methods, which we'll look through in the next few pages. So first is LRAM, which stands for left endpoint. So with this, we can see we have a curve here. And we're going from interval to A to B. So at set changes in X between A to B, we are going up to our curve and drawing a horizontal line over to our next interval and doing the same thing over and over, creating a whole bunch of rectangles, which, as you can see, are based off of where the left side of our rectangle touches our curve, hence the name LRAM, or left endpoint. Now, as you can see, if we get area of this plus area of this plus area of this plus area of this, that's going to approximate our area under the curve from here to here. But obviously, it won't be the exact value. It's only an approximation because we're missing this area, this area, this area, and this area. Now, similar to left endpoint, we also have right endpoint. So this is the exact same graph, but instead of going off of the left side of our rectangles, we're going off the right side and going over. So in this case, this graph, we'd actually be overestimating our area because we've got, for example, this area, this area, this area, and this area, but still decent for getting an estimate. We also have what's known as MRAM. So this is midpoint. So with our intervals, as we're going from A to B, halfway through each one, we're going up, meeting our line, and then drawing a horizontal line. So as you can see, this is also estimating because we are missing some area here, but we're getting extra area here, and they won't always balance out. And like I mentioned, we're using the midpoint of each of these subintervals. Okay, so first example, we're going to approximate variant of the curve y equals x squared plus 2 from x is 0 to 2 using LRAM, RRAM, and MRAM with 4 equal subintervals. So we'll do this over the next few pages because we'll do LRAM on this one, RRAM on the next one, and MRAM on the final one. Now, we already have, in this case, our subintervals drawn out on here. So we can see that we're going from 0 to 2, 4 equal intervals. So each interval is 0.5. So this would be 0.5 here, then 1, then 1.5 here. And if we look at this, this is a whole bunch of rectangles. Now we know our area for rectangle is our length times our width. Now for each rectangle, our width is just going to be how far across the rectangle is. So 0.5 for width for that one, 0.5 for width for that one, 0.5, 0.5. We can also write that as 1/2. Now, solving this, I'm going to say L4 because it's area for 4 intervals is equal to 1/2 times f of 0. Because f of 0 would be our y value at this left side of our interval when x is 0. Plus, so that's our width times our length or height, 1/2, which should be our width again, times f of 0.5, because that's going to give us this height here. And then plus, we've got 1/2 times f of 1, because that's giving us our height of this rectangle, plus 1/2 f of 1.5, because that's the height of this rectangle. Now what we can see is every term here is 1/2, so we can factor that out. I also tend to like to work in fractions, so therefore I'd have 1/2 times f at 0 plus 1/2 times f at 1/2 plus 1/2 times f at 1 plus 1, or sorry, I mentioned at the beginning of this line that I was factoring out for 1/2 because every term had it. So I have 1/2 times f at 0 plus f at 1/2 plus f at 1 plus f at 3/2. And now we'll fill in what these are. So for example, if we've got 1/2 times f of 0, we're just plugging 0 into this equation, and that gives us 2. Then same thing, plug 1/2 into this equation, and we have 9/4. Plug 1 into this equation, and we get 3. And then plug 3/2 into this equation, and that gives us 17/4. So that gives us 1/2 times 46/4. Now, simplifying this gives us 23/4, or we can write that as 5.75. So that was our L round with that equation. Next, we'll do our R round. So with this same idea, each of these intervals has a width of 1/2, but now we're basing it off of the right side of our intervals. Now, because we're looking at the right side, I would probably start by labeling as R. So R of those four intervals would be 1/2 times the height of this first one, which would be f of 1/2, plus 1/2 times the height of the second interval, which should be f of 1, or f at 1, I should say, plus 1/2 times f at 3/2, plus 1/2 times f at an x value of 2. Now, once again, we can factor that 1/2 out. So we've got 1/2 times f of 1/2 plus f at 1 plus f at 3/2 plus f at 2. Now, once again, we would just substitute these x values into our equation. Some of these we already calculated with the last example. So f of 1/2 from that last one we already knew was 9/4. F of at 1 we knew was 3. F at 3/2 we knew was 17/4. And then if we substitute 2 in for x here, that gives us 6. So that gives us 1/2 times 31/2, which gives us 31/4, or 7.75. So this one gave us a higher number, which we should expect because we can see that we are including some area that isn't included under our graph, where the other one, we were missing area that wasn't under our graph. Next, we'll look at MRAM. So we're going to do MRAM with this one. Now we know that this point here would be 1/2. This one was 3/2. But because it's MRAM, we're looking at the middle. So we would, halfway between 0 and 1/2 would be 1/4. Halfway between 1/2 and 1 would be 3/4. Halfway between 1 and 3/2 would be 5/4. And halfway between 3/2 and 2 is 7/4. Now, just like the last ones, these ones have a width of 1/2. So I've got M of 4 is 1/2 times F at 1/4 plus 1/2 times F at 3/4 plus 1/2 times F at 5/4 plus 1/2 times F at 7/4. Now, just like with the previous ones, we can factor the 1/2 out. So we've got 1/2 times F at 1/4 plus F at 3/4 plus F at 5/4 plus F at 7/4. Okay, so that gives us 1/2 times 33/16 plus 41/16 plus 57/16 plus 81/16. Going through and simplifying that gives us 1/2 times 212/16. Which simplifies down to 53/8. And we get 6.625. Now you'll notice this is between our LRAM and RRAM, which will most of the time be the case. Okay, so that's utilizing rectangular approximation. We're now going to talk about trapezoidal approximation. So to approximate the area under the curve for the interval A to B, our trapezoidal approximation gives us our h/2 times y0 plus 2 times y1 plus 2 times y2 plus 2 times y3, continuing on till we get y subscript n, where h is our b value minus a divided by n. So our b would be our value from here, our a is our value from here, and n is our number of intervals. Now how this works is we break it up into a whole bunch of intervals between A and B. Depending on the question will be a different amount. You're usually told how many. Our starting height here would be y, not well, our final would be y to n, and we are increasing by 1 each time. So we've got y1, y2, y3. And the reason why this is called trapezoidal approximation is because we are essentially creating a whole bunch of trapezoids, which is what that equation is calculating the area of. Because, for example, we'd have a trapezoid here, a trapezoid here, a trapezoid here, a trapezoid here, trapezoid here, trapezoid here, a trapezoid here, another here, another here, another here, and another here. So it still doesn't match it perfectly, but it does follow our curve very nicely. And essentially, the more trapezoids we get, the closer it's able to follow it. So for example, use the trapezoidal approximation method to approximate the area under the curve of y equals x squared plus 2 from an x value of 0 to x equals 2 with 4 equal subintervals. So this has already been drawn out for us. So this here is our graph of y equals x squared plus 2, and it's been broken into those intervals. Now for trapezoids, that's going to create would be something like this. So we can see it still doesn't match perfectly, but it does match our curve reasonably well. Now we'll use that equation from a previous page. So we've got Tn is equal to h over 2 times y naught plus 2 times y1 plus 2 times y2. Now, before we get too carried away of how many have it, we can just label these on here. So this is y naught, this is y1, this is y2, y3, and y4. So we've got plus 2 times y3, and then our last y is y to 4, so that's just going to be plus y4. Now, we have to calculate what our h value is. Our h value is equal to b minus a divided by n. So in this case, x was our b value, x equals 2 as our b value, while our a value was 0, and then we did 4 equal intervals in this case. So that gives us h is 1/2. So in this case, we're looking at 4 intervals. So we've got t of 4 is equal to 1/2 divided by 2 times our y naught, which would essentially be our f of 0, plus 2 times y1, which would be f at 1/2, plus 2 times our y by 2, which would be 1 plus 2 times y3, which would be f at 3 over 2, plus y4, which would be f of 2. So we'll substitute values in. So we have 1/2 divided by 2 is 1/4. F of 0 is 2. And then we've got plus 2 times f of 1/2, which gives us 9 over 4, plus 2 times f at 1, which would be 3, plus 2 times f at 3 over 2, which is 17 over 4, plus our f at 2, which is 6. So we'll just simplify this a bit more. So we've got T4 is equal to 1/4 times 2 plus 9 over 2 plus 6 plus 17 over 2 plus 6. And going through and simplifying that gives us 27 over 4, which is 6.75.